we want to talk about the direction, the form, the strength, and whether there are outliers. These are four things that we always want to talk about when we're talking about scatter plots: strength, form, direction, and outliers. Okay. Maybe you want to create an acronym, something that means something to you with that, but just remember that those are the four things we want to talk about. Strength is how strong it is, based on how close the points are to an imaginary line that you would draw. The form, is it linear or not? The direction, is it positive or negative? And whether or not there are outliers. So for this one, our strength is, I would say, moderate to strong, depending on if you were to draw a line, you're trying to draw a line of best fit that you think if you drew it, it would draw. We'll talk about the criteria for making this, but basically we want to minimize the square distances from each of the residual points, which probably doesn't make sense right now. But the dots are pretty close in line, so I would call this strong. It is linear. It is positive because the points are going up and to the right, and there aren't really any outliers. This point might have some leverage, but for now we're okay. And by leverage, I mean that this point right here might cause your graph to change the slope. And an outlier would be outside of the data set. That is a far departure. The linear correlation coefficient, R, is a measurement that we use to determine how strong something is in terms of a linear relationship. This calculation, we don't ever really want to do by hand because you are summing each of the x values, distance from the means divided by the standard deviation, which you might recognize as a z-score, and then you're doing it for the y's as well. You're summing each of their products. So you find each value's distance from the mean divided by the standard deviation, each response value from the mean, and divide by that standard deviation, and then multiply the two together, and then add all of that, and then divide by n minus 1, which is atrocious. We don't want to do that. So we want to give, let's not get bogged down with the calculations. This is going with page 61, but we want to give an interval to represent the ranges of possible values for R. Okay. This should be probably not necessarily in a question mark, but a period. R can go from -1 up to +1. -1 means a strong negative relationship. And +1 means that there's a strong positive relationship. And some books use different values to determine whether something is weak or strong. I would say that this would be, we're looking at -0.25, -0.5, -0.75, 0.25, 0.5, 0.75. Typically, strong is between 0.8 to an R value of 0.8 to 1 or -0.8 to 1. So right about here. This would be something we would consider strong. This would be moderate, from about -0.8 to -0.5 or 0.5 to 0.8. And then we would consider from 0.5 to 0.3 weak. And anything in the middle between that would be really no relationship. So a negative R value tells us that there is a negative association. A positive R value tells us that there is a positive association, meaning the graph goes down to the right, positive goes up and to the right. This would be a positive association. What values of R indicate a weak relationship? I would say between -0.3 to -0.5 or 0.3 to 0.5. Stronger negative relationship would be negative 0.8 to negative 1. I think your textbook might say negative 0.5 to negative 1. Value stronger positive relationship. I would say based on most textbooks from 8 to 1, but I think your textbook says from 0.5 to 1. Again, the negative 8 to negative, or the 0.8 to 0.5 range is sometimes called moderate depending on the textbook you're using. Okay, what do we predict about the linear correlation coefficient of R? Well, based on our picture, it feels like our data is pretty close to the line. That seems to be a strong relationship. So I would say that it's probably between 0.8 and point, 0.8 and 1. And then we're going to calculate that. So the way in which we do that is we do stat, regression, simple linear in StatCrunch. Stat, regression, simple linear. Our input was initial drop, and our duration was our y variable. There are a couple of other things that you can do here, determining what kind of properties you want, what you want to say, whether we want to predict or not. We'll use those later in the semester. So here we have our R value is calculated, and we're going to pull that information to answer some questions. Okay, our value of R is right here. It's called the correlation coefficient, and it's 0.9056625. Well, we can say it's about 0.906, and that is strong. The value of R is unchanged by units. Okay, that's really important. It doesn't matter if I go from Fahrenheit to Celsius or not. It's just the R strength doesn't change when you're changing between units. Two students conduct a study to investigate the relationship between forearm length and height. Maria measures the subjects in centimeters. She sees there's a linear relationship. She calculates the correlation coefficient and gets 0.86. John measures the same subject in inches. He also calculates the correlation coefficient. How do you expect the correlation will be for John's measurements? Well, we're unchanged by units, so John's correlation should be the same. It doesn't matter if I'm in units or centimeters, you're still going to have the same relationship. The correlation R measures only the strength of a linear relationship. It does not measure any other type of relationship. Which scatter plot has a correlation coefficient close to 0, but also has a strong relationship between the variables? Okay, this is linear. This is like just kind of spread out all over the place. This is quadratic. So that is going to have a strong quadratic relationship, but it's not going to be a linear relationship. It's quadratic. So one does. One has a strong relationship that is not linear. This brings us to the fact that the correlation coefficient of R is not enough to determine whether a relationship is linear. You can have a high R value with a graph that might be exponential. Let's see, if I had something that looked kind of like this, I could probably get a line to it that would get pretty good for my R value. However, without seeing a picture, I'm not really sure if it's linear or not unless I can see the picture. And the correlation coefficient can be heavily influenced by outliers. Let's say I have some data, and I've got a line here, and then I add a new point in over here. That's going to affect my slope. That's going to make a difference. Okay. A study of tutoring services at a community college shows a strong positive relationship or positive association between time spent in a math lab and the math exam average. Decide whether or not each statement is valid. Students who spend more time in the math lab tend to have higher exam scores. Well, we're talking about a positive relationship between time in the lab and math exam. Positive relationship means as my scores go up, or as my lab time goes up, so will my scores. So students who spend more time in the lab have higher exam scores. That is true. This is valid. The tutoring services in the math lab are improving student performance on math exams. I'm not really sure if that's true or not. This is not a experiment where we know for sure we've imposed some sort of treatment and it's the math lab. We don't know that. To improve student performance in math classes, the college should require students to attend the math lab. Also not valid. There are other ways that this could possibly happen. That's all I have for you today.